All right, there's one more standard ideal filter to know about, an ideal band stop filter, BSF. Okay, and band stop means it's stopping a particular band of frequencies. So you can see that right here where this notch goes down, any kind of signal that's between omega L and omega U will get a gain of 0 and get blocked. So band stop filters are very common when we know there's some interference that's causing us troubles at a particular frequency. So we build a band stop filter just to block it. Okay, so that's a band stop filter. All right, finally, the last topic is just real quickly, how good are these ideal filters that we talk about? Well, they are good, but they have one problem. How practical are they? And the short answer is they're really not very practical. All right, so let's talk about the long answer. Okay, and to make the point about this, think about an ideal low-pass filter. Okay, it's got constant gain in the passband. It's got these brick wall responses right at the edges of the passband. We call that a brick wall. Okay, so let's look at this thing. In class, we did the inverse discrete time Fourier transform to find the impulse response function. Okay, and we got this, assuming that there's no delay or anything. If there were delay, we would have something that looked like that, which would be fine. This is a constant group delay, and so we would have a impulse response that looked like that. So that would be fine. So here we've tried to make it a little bit practical by recognizing that all real systems have some sort of delay. And so here would be the impulse response function. However, when we plot this out, and I've kind of drawn the envelope here because it's easy to draw. It's like a sinc function, right? But in fact, it's a discrete time signal with made up of these discrete points every sample. Okay, can you see a problem? So, and you should immediately see a problem. Remember, this is the impulse response function. This is the response of the system to an impulse coming in at n equals 0. And the problem with this is the impulse happens at n equals 0, but we're starting to get output from the filter before the input ever happens. Okay, so this is non-causal. So all of this stuff, we don't know how to deal with it, right? We can't build in real world a non-causal system, so we can't implement it. The other problem is stability. If you might remember that one of the requirements for stability in a system is if you add up the absolute values of the impulse response, it has to sum up to be less than infinity. But it's not too hard to show that for a sinc function, that doesn't happen. It adds up, it approaches infinity. So not only is this filter non-causal, but it's unstable. So even if we could build it, it wouldn't work. It would blow up. All right, and the whole reason for this bad behavior is traced back to this brick wall response that we ask for. If we want brick wall response, the only way we can get it is if we can build a non-causal filter, and if we don't mind it being unstable. All right, so in practice, that's just not something that's going to fly. All right, so what do we do? I mean, we obviously live in a world where we use filters. Filters are very important. So what do we do? And the answer is we have to accept the fact that we're going to have non-ideal filters. Okay, something is better than nothing. Well, one way we can make h of n realizable is by delay and truncation. If we delay this filter long enough, if we delay the impulse response far enough, you know, these ripples are starting to get pretty small. And so maybe if we delay it long enough, we can delay it so most of the response is in positive time, where it has to be it needs to be in this positive time range in order for it to be causal. But to make it causal, we have to set all of this stuff equal to 0. Okay? And we still can't implement this unless it's finite in range, because you remember how we do this. We say that the output is equal to the input involved with h of n. Well, if this is infinitely long, this is going to be one tough convolution. So we set it equal to 0 on this end as well. So these ripples of the seq function are getting small. Let's just set them equal to 0 and hope they don't cause much trouble. Okay, so now we can build a realizable filter. It's got some delay, but obviously we've done something to it, right? It's no longer the ideal filter it started out as. And here's what happens. If we find the frequency response of this non-ideal filter, we find that the magnitude looks like this. And if we do it just right, the phase looks like this. All right, here I've summarized. It's no longer brick wall. We've got a slope here, right? Instead of a straight up and down response at this edge, it's got a slope. Okay, so it's not brick wall any longer. There is ripple in the passband. Okay, that's ripple. That means that some frequencies are going to get less gain, like this frequency, and some frequencies are going to get more gain. And that's a kind of amplitude distortion that we don't really want. Look at here, in the stop band where we're trying to block noise, some of that noise is going to get through. This is not exactly 0 in the stop band, right? So we got non-zero response in the stop band. We've got transition bands. Since this is not brick wall response, we have to, as engineers, say, all right, there's a region here. Let me make this a different color. There's a region here where we're going to call this a transition band. As engineers, we got to say, all right, I can't give you perfect, but I'm gonna make there be a region where we just don't care. That's called a transition band. Okay, and I can make that transition band as small as I want, but I have to pay for it, as we'll discuss later. Well, the interesting thing about this is we can still have linear phase. Okay, we can still have linear phase, and that's pretty cool, because of all of the ideal things that I know of, this is one of the very few that we can still accomplish. We can build a linear phase filter as long as we do it with discrete time systems. We can't do it with analog systems, but we can do it in discrete time type processing. All right, so here's the bottom line. We cannot have ideal gain response. It's just not practical, right? This is what we wanted. We want constant gain in the passband, 0 in the stop band. We can't do it. But we can have, I emphasize this, we can have linear phase in the passband. So that is something we can accomplish. We can build a filter that has no phase distortion. And you know, without this property, we wouldn't have our cell phones and our digital televisions. We'd be lost in the woods. Okay, only discrete time systems can do this. Analog systems can only approximate linear phase. Well, that's the end of this discussion. And I'm sorry if it ran a little bit long.